All right, welcome to our lecture video one, part two, if you want to think of it that way, of Monday's lecture, which is Monday, April 3rd, where we're discussing various perspectives that we have available to us to define and characterize and identify what an acid is exactly. We just discussed the first definition, which is the Arrhenius definition, which says that acids are anything that contribute H plus into solution when dissolved. And as I mentioned before, that's kind of our definition of like what an acid looks like how you could identify an acid. You say, oh, does this have an H plus that could be put into solution? However, this next definition, the Bronsted-Lowry definition, describes better what an acid does chemically, like how an acid behaves. So Bronsted-Lowry definition of acids states that acids are proton donors in some kind of reaction. And remember, when I say proton here, I mean my acidic H plus. So for example, if I were looking at the reaction of hydrochloric acid and sodium hydroxide, if these were to undergo a double displacement where our cations get new anions, I would see that more simply the formation of HOH, which is liquid water, and sodium chloride, which is aqueous, right? Sodium and chlorine come together to form a soluble compound that's using our solubility rules. Feel free to reference those if you would like. And if I were to look at the net ionic equation for this, I would find that I would have my acidic proton being donated or given to that OH minus to form HOH or H2O. So if we are proton donors, meaning if that H plus is given to something else in a chemical reaction, then we are a Bronsted-Lowry acid. This definition of acids, this Bronsted-Lowry definition, this is going to be kind of like the main definition of acids that we utilize in Chem 210, simply because we are mostly concerned about acids and what they do when they react with something else. So when we talk about what an acid does in reaction or what it does in solution, we're talking about things that donate or give up, or I guess I can't think of another word for donate off the top of my head, so donate an acidic proton or a hydrogen ion to something else in reaction. So that's a Bronsted-Lowry acid. Now, lastly, as mentioned, this is something that's going to be more important in organic and biochemistry, but you will see this pop up again in your science career. We have our third perspective of what an acid is, and that is our Lewis definition. And you might recognize that name Lewis because Lewis was our guy who was all about those Lewis dot structures, right? In fact, most of Lewis's career was concerned with characterizing what electrons are, what they're doing, how they're interchanged or shared or swapped in chemical reactions or in chemical bonding. So it makes sense then that when we talk about the Lewis definition of acids, that instead of thinking about what's going on with these acidic protons or H plus ions, rather we think about what's happening with electrons. So according to Lewis, acids are electron pair acceptors in some kind of reaction. We also have another word that you'll see pop up in OChem for this idea of like an electron pair acceptor. We call these electrophiles. So electro meaning electron, philic, right? That means to love. So electron lovers, these are things that are attracted to electrons. And there's a little bit more detail to add to this Lewis definition of what an acid does in solution. So it's not simply that acids are electron pair acceptors in reaction. Rather, once those acids have accepted those electron pairs, our Lewis acid forms a coordinate covalent bond with the substance that is the one that's donating that electron pair in the first place. So I think this is best illustrated by an example, even though, like I said, we're not really going to be talking about Lewis acids in at least 210. So let's look at the reaction of BF3 and ammonia. So this reaction is a synthesis reaction. We form BF3 and H3, which is ammonio trihydro. Oh God, don't ask me to do this. I'm not an organic chemist, but we make those products. Now, what is it about this product that has electrons being donated versus accepted? What's the Lewis acid here? Like, how would I be able to know whether this is a Lewis acid or not? And what is going on with this concept of a coordinate covalent bond? So if we're gonna be thinking about what electrons are doing, according to the Lewis definition, we should probably be drawing some Lewis dot structures so that we have an idea about what's happening with electrons in this reaction. So I've got BF3, which you might recall from our chemical bonding workshop, is a trigonal planar molecule that is an exception to octet, like such. And then we've also got our ammonia, which is a trigonal pyramidal. I'm just drawing it on its side, like so. And then the product that we form is going to look like this. We are going to have now local trigonal pyramidal geometries around both our boron and our nitrogen. And the reason why we went from being trigonal planar in the BF3 to this trigonal pyramidal is because we've now created this electron group between boron and nitrogen. And remember, electron groups repel one another. So let me just fill in my remaining valence electrons on my fluorines. All right. So again, what on earth makes this an acid-base reaction? Or even just like, where's the acid? So if we think about what's going on according to the Lewis definition, acids are electron pair acceptors. So let's identify the electron pair that seems to be donated in this reaction. So because this ammonia is the only thing that has these non-bonding lone pairs of electrons, these are going to be donated, well, not fully donated, but you'll see, donated to the boron, and in doing so, creates a covalent bond that we call a coordinate covalent bond, where a coordinate covalent bond is simply a covalent bond where the electron pairs that are involved in a bond come from just one species. So normally when we think of a covalent bond, we think of some element A and some element B, and they're like, oh, hey, yeah, we could share. This would be a normal covalent bond. However, a coordinate covalent bond is if we had element A with nothing, and then element B with two lone pairs, then A and B are still going to share. It's just B is the one that's wealthy in electrons. So these shared electrons come all from B, making a coordinate covalent bond. Now, is this something that I'm going to expect you to even try to look for in Chem 210? No. Will we see it in Chem 220? A little bit. This is, again, a really OChem perspective of what's going on with acid-base reactions. But it's good to point out to you because even though we are going to predominantly focus on both our Arrhenius and especially our Bronsted-Lowry definition of acids, that doesn't mean that acids are only things that involve H+, right? That hydrogen ion is not the only thing that an acid can be. Notice in this reaction, here the BF3, this is our Lewis acid. This is the thing that accepted the electron pairs. And there's no hydrogens involved that I can tell in solution here anyway. And besides, these are liquids, not aqueous. So these are our three functional definitions of acids. Again, we are going to pay most attention to the Arrhenius definition and the Bronsted-Lowry definition. And what we're going to do next is we are going to delve into definition of bases. And we're going to use, again, these same kind of three frameworks where we have the Arrhenius definition describing like what we are in terms of how we look, generally how you can identify based on just like what's present in the compound, what makes us a base. Then we are going to look at our Bronsted-Lowry definition, which describes what bases do in a chemical reaction. And then we are looking at the Lewis definition of bases, which again is a definition of what bases do in reaction based solely on what's happening with their electrons. So that's coming up in our next video in just a moment.